Hi, my name is Samir Shende, and I will be describing the Extreme Scale Scientific Software Stack, or E4S, today. There are two challenges that I would like to address today. The first is that with our hardware getting more and more complex, it's getting harder to accurately measure and optimize the performance of our HPC and AI machine learning workloads. The second problem is that as our software gets more complex, it's getting harder to install the tools and libraries correctly in an integrated and interoperable software stack. And to address these issues, we present the ECP's Extreme Scale Scientific Software Stack. Now, ECP has three technical areas. There's the application development, software technology, and hardware and integration. And our goal is to deliver expanded and vertically integrated software stack to achieve the full potential of our exascale computing platforms. There are 70 unique products that span a number of areas, from programming models and runtime, to math libraries, to tools, to data and visualization. And these form the crux of our software stack. We work on products that applications need now and in the future. And we have a range of products in this software stack, which includes MPI, OpenMP, OpenACC. There are performance portability libraries that allow you to write performance portable codes. There are performance evaluation tools such as PAPI, the Tau Performance System, and HPC Toolkit. There are math libraries such as Trilinos, BLAS, PETC, sundials, sparse solvers. There are I/O libraries such as HDF5, MPI-IO, Adios, and data and visualization tools such as ParaView. So we have many of these ST or software technology products that ECP is developing, and they are grouped into these software development toolkits or SDKs that group similar products together and ensure interoperability and compliance to policies of SDKs. And then E4S consists of multiple SDKs put together. So E4S aims to deliver a modular, interoperable, and deployable software stack, and to deliver expanded and vertically integrated software stacks to achieve the full potential of our platforms. Our goal is really to lower these barriers, lower the barriers to using software technology products. And we also have performance evaluation tools that will allow you to observe the performance of these applications. And our goal is to also enable uniform APIs where available. You can download E4S from our website, e4s.io. It's a community effort. It's a community effort to provide open source software packages and allow them to be deployed in an easy to use manner. And we have support for both from source builds as well as containers of a broad collection of HPC software packages. So E4S primarily exists to accelerate the development, deployment, and use of HPC software and provide these HPC packages in an easy to use manner. These are the areas that I described earlier, but really ECP software technology SDKs span a number of different areas, including programming models and runtime, where they have packages such as Legion, Cocos, Raja, MPI, like MPitch and OpenMPI. We have support for compilers and LLVM compilers and other projects that use them. We have tools and technology, which includes Tau, HPC Toolkit, Caliper, PAPI. We have XSDK, or the math libraries, which include packages such as SuperLU, Trilinos. We have support for sundials, PETC, and we have analysis, visualization, and reduction operations with ParaView. We have Visit, data management, IO services, and also ecosystem at large applications. So there are a number of different areas that that these SDKs cover. And these SDKs are typically put together in this form with math libraries, data and visualization, programming models, and then we integrate, build, test, and deploy them. So E4S is a curated release of software technology products. And E4S is based on the Spack package manager. You can learn more about Spack from this spack.io webpage. We have binary build caches for bare metal installs. So we support multiple platforms, including the IBM PPC64 LE platforms. And we have container images that are available on Docker Hub and available for download from the E4S website. And these include the pre-built binaries of ST products, where we have both base images, which allow you to create your own custom image, and also full-featured containers, which have a number of these packages pre-installed. And they all come with GPU support so that you can use the CUDA and NVIDIA GPUs through the PPC64LE platform. Now we also have recipes for creating custom images. We have support for building E4S images in GitLab. We also have a validation test suite and a VirtualBox image with support for multiple runtimes. And we also have an image on AWS. So it's typically released twice a year. And you can find the latest version 1.1 release, which includes over 45 full release products. And it has support for GPUs. So if you go to the Docker Hub page, you can just directly pull from there using the ECP E4S Ubuntu 1804 E4S GPU. And it has support for CUDA 10.1.243. As you can see, the PPC64LE platform in this full featured release. And if you look inside the image, here are all the packages that are installed from the software technology portfolio. And there are many more. And we have support for NVIDIA GPUs. And this illustrates that we have support for AI ML frameworks like this. In fact, let me just jump right in and show you a demo of this. This is a Singularity image, and I can just load it using this Singularity command. And I can say Python, and you know, it's difficult to install packages like TensorFlow, Keras, PyTorch, and these are pre-installed for you. And if you see the GPU availability, you can see that on this PPC64LE system, I have access to V100, 4 of these V100 GPUs. And a number of other packages, such as I could say PyTorch or CV2 or Matplotlib. The most commonly used packages are all there in the distribution. So you can use it on this AC922 system. Here is an example of using Python. So if you are an AI or machine learning user, you don't need to install all these packages from source. You can just download a single GPU-enabled image and deploy it on your system without any special permissions or privileges. You can download the GPU image directly from our E4S webpage or do a Docker pull, as I mentioned, and you can use it with Docker. We are also enabling other custom images. And here is an example of a TensorFlow 2.2 image with CUDA built in, and one that can be downloaded like this for PPC64LE. So if you're trying to build this TensorFlow 2.2, then you can just get a Docker image from the ECP E4S area on Docker Hub. Here are other images. This is with TensorFlow with CUDA 10.2. And these are custom images that we have built, which you can just pull directly like this. Now, our E4S distribution is built upon the Spack package manager. And we use this for the software delivery. It provides the ability to specify different versions of the software packages that are or are not interoperable. And it's a build layer for a large collection of software tools, and is the primary platform for deploying our tools and libraries. And the motivation for this is that really scientific software is becoming extremely complex. Here is the dependency tree of NALU, a generalized unstructured parallel low mark flow system. And you can see that NALU depends on Trilinos, which depends on Parmedis, which depends on Metis, which depends on CMake, and a number of packages. So our software is becoming very complex. Here is an example of Deal2, a C++ finite element library. And you can see that to install all these packages correctly can be challenging. Here is the dependency tree for R minor, and you get the idea that our packages are becoming really complex, and even proprietary codes are often based on many open source libraries. All these nodes in blue are open source packages used by Aries. And the Exascale Computing Project is building an entire ecosystem with over 15 applications with 80 software packages, with multiple platforms and compilers and programming models. So if you use 2 or 3 different versions of each package, this combinatorial explosion will lead to like over 1 million combinations. And every application has its own software dependency. So we are now at a point where developers, facilities are dedicating many FTEs just to building and porting the HPC packages. And this is not scalable. And often this trades reuse for usability and usability for performance. So we must make it easier to rely on other people's software. But how do we install software? How do we install software on a supercomputer? Well, we start with downloading all the 16 tarballs you may need for an application, and then we start building it manually, one by one. And it looks a little bit like this, where we configure, we build, we fight with the compiler, we tweak the configure arguments, we configure, make, install, and then finally, we are able to build the application. And when we run the code, if it seg faults, we start all over again. And there has to be a better way to deal with the complexity of installation. Now, you may ask, what about modules? Well, modules don't install the software. They are just a way to modify your environment so that you can put LD library paths and paths correctly. But somebody else has to build the software that modules export. So that's where the Spack package manager comes in. It's a very easy to install package manager. You can just do a git clone. You can set up your environment, and then you can just install the package. You can say Spack install tau, and then tau and its dependencies are installed within the Spack directory structure. But what is interesting is that it can support many variants for the same build. You can have different compilers, you can have different MPI implementations and build options. So it provides a spec syntax. You can say, for example, Spack install tau, and it will install tau performance system. But you can also say Spack install tau at 2.29.1. It understands different versions. So within the same Spack, I can have two different versions of tau installed, and I can specify a compiler for one. I could say, but use the GCC 730 compiler using the percentage symbol. I can also specify variants and build options such as please use Python with pthreads and MPI, or when you use MPI, please use the MVAPitch 2, which supports the InfiniBand hardware version 2.3, but don't use the wrapper RPath argument, so that you can take the build of that and move it to a different system, the binary, and then launch it. You can say Spack find, and then it will show you all the packages that are installed. And this is really a very interesting way of using software, where you can say Spack find, and it will show you all the packages that are installed over here. Here's the mpitch package 321. You can say Spack location -i mpitch, and then it will show you the location. So if you say which MPI CC, it picks up the MPI compilers from this particular location. You can get more information about Spack from this web page, but it is central to ECP's software strategy. Now we provide in E4S Spack build caches and container build pipelines. And there are recipes that you can download from our GitHub page, and there are build caches that we have created. What this means is you do not need to compile the package from the source code. You can simply point to this E4S build cache, and then it will download the binaries for your platform. Here we see that we have now accumulated over 8,000 PPC64LE binaries, and you can search for the Spack packages if you go to this web page, and you can pick an architecture, and within that you can pick different operating systems like Red Hat 8.2 or Ubuntu 2004, and then you can see which package is available. And if you just say Spack mirror add E4S and point to this cache.e4s.io and build cache keys -it, then you will be able to just say Spack install, and it will pick up, in this case, say Amrex package from the build cache and download it. We also have GitLab runner images on GitHub, where we have, for example, an Ubuntu 18.04 image for PPC64LE. You can see that it has a number of downloads as it's being used by our GitLab runners, and many different operating systems are supported. We have base images for PPC64LE, where you can see there's Ubuntu, RHEL, as well as CentOS. We use the UBI, Universal Binary Image. And the advantage of using UBI is that if your software stack is based on UBI and it's running on a Red Hat system, then the support of Red Hat extends all the way to the software stack used in UBI. So it's a supported image. In E4S, we also have reproducible Docker recipes that you can find over here, in this case, on how to build it. And we have a singularity image, and I just showed you. To use this image, you can just go to the E4S webpage, to the download link, download this singularity file, just one file, and launch it with the --NV for accessing the GPU. Just launch this image with WinBash, and then you can already have all these packages in your area. Here are build pipelines for creating Spack build caches, and how we add another package to this. You can see that there are multi-stage builds. This is a build that's happening on an IBM system at Oak Ridge National Labs. It's PPC64LE, and you can see how these jobs are all staged in the build pipeline. We also have a test suite. Now, this is very interesting because we are assembling all these packages, but we have a way to validate that they do what they claim to support. So we have examples that we build and we run and get a pass failure output from different tools and libraries. And then we use that to create these reproducible container builds using the base images. Here is a virtual box image where I can use this image and get familiar with different types of container runtimes. It has Docker, Singularity, Shifter, Charlie Cloud, and it has Spack pre-installed. You can also use the image to launch an E4S image like I just showed you, and use the bin bash and then use the Spack from within this. So to summarize, I'll say that E4S is not a project that has started from a scratch. It is building on top of previous effort. It is leveraging the work of many other tool and library developers. The precursor work done at the University of Oregon and Paratools Inc. on HPC Linux contributed to this. There is the Ideas Classic XSDK project, the original SDK that's still continuing under the ECP. And of course, Spack, the package manager, predates E4S. We are working to improve support for GPUs and visualization tools. We have a DOE LLVM effort where we are putting together multiple research projects that are funded by DOE and have a single DOE LLVM repository, and we'll be doing some additional CI testing and facility deployment with this. We also have a project called supercontainers, and we are studying the scalable startup of these containers and also improving the launch of MPI applications. The idea being you can build on one machine, take the binary to another supercomputer, and then launch it using the E4S container launch tool so that you can switch the MPI inside the container with the native MPI that may be supporting high performance interconnects, such as the Mellanox InfiniBand that's available on systems such as Summit and Sierra. So using the MPICH ABI or application binary interface, we can do this substitution. In conclusion, I'll say that it provides a well-integrated software stack for AI, ML, and HPC, and assists in source-based builds from our binary cache and containers. So I would like to say that E4S is not a closed system for taking contributions only from DOE software development teams. It's an extensible open architecture software ecosystem that accepts contributions from US and international teams. It's a full collection of compatible software capabilities, and it represents a manifest of many a la carte selectable software capabilities. You can think of it as a vehicle for delivering high quality reusable software products in collaboration with others, and a sort of a conduit for future leading edge HPC software, which targets the scalable next generation computing platforms. The work that I presented happens partly at the Performance Research Laboratory at the University of Oregon. We are based in Eugene, Oregon. And I would like to thank our sponsors, the Exascale Computing Project, for their support of this project. So with this, I'll take any questions or comments that you may have in the QA. And I can show you some examples as well. Here is an example of Trilinos. Now, I can start from a scratch and say Spack load -r Trilinos. this loads Trilinos and all its dependencies using the Spack package manager. If I say Spack location-i Trilinos, then I can see this directory in the Spack package. I see that it has a lib directory, and it has a number of these libraries, solvers that are pre-installed. I can say compile.sh, and I am compiling with these libraries. You can see that this package uses a number of libraries. If I were to just say LDD on this Zoltan binary, well, that's about 113 shared objects that are being used to just build this. And if I were to run this, I can use MPI, I can launch this solver. I can even use TOW to profile this application. Here I'm just saying profile the IO in the application, profile the kernels, and there are files that are produced for every thread of execution where you can see the MPI, you can see which files and ports were accessed. And I can, of course, visualize that. So with this, I'll see if there's any other questions we can help with. If you have any, if you need some additional information, please visit our webpage, the E4S.io, and please get in touch with us. I hope you find this collection of HPC tools and libraries useful in your work. Thank you very much.